Moving on to an extra question, a fourth question here. We're going to look at this sort of conical circular motion, but it's within inside a sphere. Well, this particular one is a hemisphere, but it's exactly the same treatment that you would make if they're talking about inside a sphere. It's the same thing. It's just, I suppose, easier to imagine this happening inside a bowl, maybe. Anyway, so the bowl has a radius of 15 centimeters. And it's fixed. There's a particle, a smooth particle, so again we're not worrying about friction here. It has a mass of 2, and it's describing a horizontal circle of radius r. We'll have to work that one out in a moment. On a smooth, again, no friction, smooth inside surface of a bowl. The plane of the circular motion is 3 centimeters above the horizontal surface. Okay, and you can just about see that there. You can see there's a little symbol here showing that the object is 3 centimeters off of the ground, off of the surface the bowl is sitting on. Find the normal reaction between the particle and the bowl, and show the angular velocity of the particle is 5 root g over 3. So looking at R, we can, or looking for R, we can see that in terms of the whole idea of this, the radius of the bowl is 15. So the string is of length 15, because our whole idea is in this hemispherical bowl, this string should be able to touch every single part of the bowl. So it's 15 going in that hypotenuse and all the way down to the bottom of the bowl. Now, if the circle in motion is happening 3 centimeters above that base, effectively we're 3 short, so i.e. the height of the end of the string, I suppose, if you imagine, there's no actual string there, but you can imagine, if we're looking at the previous question, you can imagine that string being there. Anyway, so the key idea is that right angle triangle that we're interested in has dimensions of 12 and r in the vertical and horizontal, and 15 is the hypotenuse. So it doesn't take a genius to work out what that radius is going to be. It's going to be 9. Okay, so let's now let's redraw this again, and let's concern ourselves with the forces acting. So, as I said, there's no actual string. What actually is causing the horizontal circular motion inside this bowl, as I said to you before in the previous lesson, imagine a Malteser sort of being spun around inside a bowl. The only thing that's causing the centripetal force is that normal reaction to the bowl, okay, at right angles basically to that bowl, is that normal reaction. Let's call it R. And there is a mass of the object, so that's a weight going down of 2g. And we can appreciate that this normal reaction has 2 components. It has the centripetal force component, and it's got the vertical component that's going to have to act against its weight of 2g. Now, if we think about those 2 components, we've got, again, our cos theta and we've got our sine theta as being the 2 components. And then we're immediately going to say, well, what's theta then? So let's just cast our minds back to the idea of a sphere, or indeed, in terms of thinking of it in terms of a circle. We can appreciate that the radius of a circle, or indeed the radius of a sphere, is going to be perpendicular to that surface. So for a circle, we can appreciate that it's going to be perpendicular to a tangent in that circle. Likewise, if you think of a sphere, if you imagine a flat plane against a sphere, then the radius from that point of contact of that plane is going to be going at right angles. It's going to be perpendicular going to the center of the sphere. So we have a situation where we can look at the angles created. If we imagine our spherical surface, and our plane to that, our normal reaction, which is what we're interested in here. And if you think of alternate triangles, that theta that we have here is going to be the same as the theta that we have here. If we're breaking our normal reaction component into two parts, we're going to have our cos theta, which is the adjacent to the angle, and the opposite will be our sine theta. So it's no different to the pendulum on the end of a string. When it's inside the sphere, the same ideas occur in terms of the use of the angle. So if we continue as we would have done beforehand in terms of looking at the horizontal and vertical separately, we'll start with the vertical. So the two forces occurring here. So we have r cos theta is equal to 2g. We know cos theta is 4/5. Now, what we'll actually do is we'll keep the we'll actually use 9.8. We'll just keep it as g. The reason being is the question actually asks for it in terms of g. We're being asked for, it's a question, we're being asked for show that the angular velocity of the particle is 5√g/3. So we're going to still use g, okay, rather than 9.8 in this instance. So r is 2.5 g. So that's our normal reaction. We can work out the actual value if we want to. Okay, it works as 24.5 newtons, but we can leave it in its sort of G format because that's going to be more use to us in the next part of this. So show the angular velocity is 5√g/3. So if we look at this horizontally, we have where the centripetal force is mr omega squared. So what is F? The force is the r sine theta, mr omega squared. So if we now fill in all the values that we know. Now, one thing to be very careful of is the measurements, the distances. It was 15 centimeters and 3 centimeters. So my radius is actually in centimeters. So it's not 9. It's 0.09 I'm going to insert into this. And if we work this through to get what omega is, omega squared, first of all, is going to end up being 3/2 lots of g, all divided by 0.18. That works out as 25 g/3. And so when we square root that, as an answer, we end up with 5 coming outside the square root and g/3 staying inside. So we have shown that the angular velocity of particle is 5√g/3, and that's rads per second.